this session. So I might have to mute you all back if the feedback gets a bit much. So this problem is one in which we're going to use the Euler's growth model, the E. And again, this thing about E, the special thing about E is it enables us to put the rate in with the exponent. So that's very helpful. And after we do this warm-up, I'll explain where the number E comes from. Okay, I'm going to do that today. So a radioactive isotope is an unstable element. So it's usually because it has more neutrons than protons, more protons than neutrons. I can't remember which it is. It might be both. But it enables the nucleus to be very unstable. So it tends to break apart and spit out a lot of energy. And when it breaks apart, you know, if you have half of the number of protons, then you're a different element. Or if, you know, you pop out a hydrogen or you pop out some kind of carbon radioactive isotope from this larger molecule, you know, there's decay products. And so half being left of this original isotope is called a half-life. And so this radioactive isotope has a half-life of 100 days. So that means in 100 days, half as much of that isotope will remain and have decayed into end products or transformed into like gamma or beta or alpha radiation, which are different types of radiation. I won't go into that. I'm a little rusty on it, honestly, but I think alpha is electromagnetic radiation, but depending on the spectrum, and I think beta is actual protons, which can cause more damage. I had one or the other, I can't remember. But anyway, so that's a little bit of science. And so what we want to do here, this first problem, is figure out, well, what's the rate per day? What's this R going to be if we have half as much in 100 days? And then the second problem, we're going to use that rate to determine how much time are we going to have to wait for this isotope to decay to the point to where maybe it's not as toxic as it used to be, right? It's the thing with nuclear waste. What do you do with it? Where do you put it? How long do you have to wait? Okay? So we want half as much. So we want half as much as original, which was A. So this is essentially, what we're going to solve. Okay, now if you want to think of it as you started with 10, half as much to N5, notice when you divide, you still get half. So this is what we're solving. We also know that this occurred in 100 days. So we know that that's 100. Okay, so now we want to reverse this to the logarithm. So we got our exponent. We got our value. And the base is E. So the log of the value is going to equal the exponent. And since it's base E, we can use ln. Okay. Now I just put it as 0.5 here. All right, so you calculate this and then you divide by 100, and what you get is negative 0.0069. And I'm going to be a little more accurate here for something that we're going to get to later. All right, so that's the percent decimal. So if you convert to a percent, 0.69% per day. Not 6.9, not 69, 0.69% per day, because this is the rate. This is per 1. Move the decimal, now you got it per 100, 0.6931 per day. Okay, and it's negative because we're talking about decay, decrease. Okay, so for the next part of the problem, we want to take this, and now we want to determine when we have 99.9% decay. Well, if we have 99.9% decay, then that means we have 0.1% left. And this basically means we have half left. So we're going to solve this problem.
Mr. Napoli, I think it would be 0.01.
Okay, now another way you could think of that, if this is how much we have left, 0.1%, then you could think of it, okay, so we started with 1,000, and now we have 1 left. And notice when you divide, you get 0.001. So that's another way to think about how to get here. And then the R is the same as the R we found earlier. That's correct, Joseph. 99.9%. That's why there's 0.1% left, which would be this decimal rate. Okay, so now we're solving this one. All right, we're very similar to what we did here. Again, we have our exponent. We have our value, and that's the base. So we're going to take the log of the value and put it equal to the exponent. Okay, so the ln of 0.001, the log of the value, equals to this exponent. And then you just divide. Now there is a button on the calculator where you do that. If, you know, there might be someone out there that doesn't know. Notice where it is. Notice right there. And the second function would also be the e, because those are related. Just like with the log button, which is right about there, the log right above it is the 10, because the log automatically means base 10, whereas the ln right above it is the e, because the base of the ln is e. So I don't know, maybe that's an issue, maybe not. I just don't want to take any chances. All right, so you divide by this, and you get 996.578 days. So that's a little bit less than 3 years. Divide that by 365. So we got to wait a little bit less than 3 years for us to be comfortable with this stuff. By that time, it'll decay. And this is when you have a half-life of 100 days. They got some radioactive isotopes out there that have half-lives of thousands of years. So how long are we going to wait? The human race will probably be extinct by that time. That's the problem with radiation and nuclear energy. All right, so we solved this problem for the R by using Euler's model. So we wanted to find the half-life. So we had half as much as we started before. So that's why this equals a half. And then we converted that to the logarithmic equation. So the ln of the value 1/2 equals to the exponent 100 times r. That's 100 because this happened in 100 days. So the time is 100. We solved this. We found out, okay, so the rate, the r is going to be this decimal. Now, what if we used the growth factor model? Well, in that case, then we would have that problem. All right, so I think we did this the last warm-up. So now if we solve this, we got to use the reciprocal exponent. So the 1/100 power. Right, and then you subtract 1. And that equals the rate if we use the growth factor model. Now you might think, oh, this should be the same thing. No, not quite. They're very close, but they're not the same thing. Okay, they're off by a little bit. You can see 3175. Now, why aren't they the same thing? That's because the underlying growth processes that these two problems are modeling are different. The way in which time is structured is different. With this problem, we're structuring it based upon days, and so this rate occurs per day. With this problem, we're using a rate, and it's based per day, but this rate is more of an average over the entire time because the growth is occurring at all points in time. All right, so in other words, when we had our growth factor and we divided by n and then did that. The reason we did this is because we were changing the period of time. So if the yearly percentage increase I, and we wanted this to be per quarter, then that would have been 4, and we would have had 4 quarters in a year, right? So we would have split the year into 4, and then we would have had that slow rate of increase. But notice that it increases right in the beginning of the next quarter, and then it stays the same, doesn't change at all. And then at the next quarter, it changes, doesn't change at all. And then the next quarter, it changes. Now, if we wanted this to be monthly, then we would divide the per year by 12, and then we would have had 12 years. And so the same thing here, right? We would have had all of our 12 intervals, and our growth would have been something maybe like this. Now, I'm exaggerating the growth, but, you know, exponential growth, right? And so the thing is, you only have growth at one point in time, and then you got to wait a whole month before you have growth. That's not realistic when you're talking about biological and scientific growth and change. Your hair doesn't just stop growing for a month and then all of a sudden jumps by 2 inches, right? That radioactive isotope doesn't wait a whole month and then all of a sudden decays by half, then waits a whole month, does nothing, sits there, okay, wait up, it's not the first of the month yet, can't change, sorry. Oh, now first of the month, boom, let's go ahead and radioactive decay. No, what happens is you get continuous growth at all points in time, which means the number of intervals gets closer to infinity. So if you went by days, then if you went by minutes in a year, then if you went by seconds in a year, the n would approach infinity to approach growth at all points in time. And if I make this 1, as this goes to infinity, as you shrink the interval down to the smallest quantity to represent all points in time, this becomes the number e. And if you want to do that, you could just do this expression, put a variable there and just, you know, see what happens. N 1,000, N 10,000, N 100,000. Normally I would do that, but this, you know, this medium isn't really built for it. So E is a model when you have growth at all points in time. It's not staggered. Man-made growth, like banking, is staggered, right? We have our quarterly intervals, we have our monthly intervals. That's completely man-made. That's not scientific or physiological, biological processes, right? Which happens at all points in time. That's what we use this for. And that's why we use this one, because we were looking at radioactive isotope decay, which is a physiological scientific process in which the decay is happening at all points in time. It's not staggered into the next interval. Okay? E is a very interesting number. Shows up in a lot of different places. It's a trip. Think of one off the top of my head, I think. This is a very famous equation. It's cool because it's got the 2 most important transcendental numbers and the 2 most important integers known to man, all in one equation. That might be plus, but I'm pretty sure that might be a plus actually, now that I think about it. Anyway. Well, thanks for the confirmation, Connor. Yeah, that's pretty trippy stuff, man. Okay, so we good? All right, let's go over the homework. Okay, any particular homework problem you want to make sure I go over, or just don't glance over?
Can you go over 43?
Okay. It's good news, or maybe I'll be getting some. But so here, this first part, probably all the way up to 27, and a little bit further, you were switching to the exponential or switching to the logarithmic. So again, the base is 3, so that's why the little number 3 by the g. The exponent's 2, so this is going to equal 2, and then the value's 9. So whatever the exponent is what the logarithmic expression equals to, right? So right here, our base is a, so you put the a there. It equals to 2 because that was the exponent. And then here, the base is e, the exponent's x, so the log base e, it equals x. You could also use ln because the base is e, right? And then the same thing over here for 17. Now you're switching to the exponential, so your base is 2, so that's why this is 2, and the log equals the exponent, so you put the 3 as the exponent, and that equals 8. Right, and then once you started to get to 25, then you had to rearrange and also solve. Now, sometimes you can interpret the log expression, sometimes you can't. You need to rearrange it to the exponential. So whatever you need to do, but the only way you're going to get a value of 1 is if you have a 0 exponent. So it has to be 2 to the 0. If you switch this to the exponential, you can interpret it that way too. Same thing here, right? In order to get a value of 25, if the base is 5, you need an exponent of 2 because 25 is 5 squared. You could also switch this to the exponential. Again, whatever the log equals is the exponent. So the log equaled y, that's the exponent. Okay, and then down here, 29, I thought was a little tricky because it had that fraction. And again, you know, you might be able to interpret the log expression for 29 as is, but if not, switch it to the exponential. So base 1/2, the log equals y, so that's the exponent. Okay, so now we want to get these two to be related to the same base, so I use base 2. Okay, and so in order to get the reciprocal, you need a negative exponent. And 31 was a little tricky because the value was a square root. So you still got the base 10. The log equals the y, so that's the exponent, and then the value's root 10, which can be written with a fractional exponent of 1/2. Okay, and the same thing, 33 and 35 in similar ways. With 33, the base was actual square root. Now, there's nothing wrong with using the square root of 2 as a base. We don't really tend to do that, but that's what they did here in this problem number 33. Okay, so then our root 2's got the exponent y equals 4. All right, so if we're going to compare these, we need to compare them with the same base, so that's why I'm using 2. Okay, so then once you get the exponents using the same bases, then you can put them equal to each other. So y would have to be 4 there. Okay, and then the same thing here, 35 and 31 are practically the same, it's just a different base. Right, so you get your base e because the ln is using base e. The y is equal to the ln, so that's the exponent, and so then the 1/2 power for the square root. Okay, and then the last part were the domain issues, and there were only 2 that I thought might be problematic, and depending on if 43 was tricky, then that was the last 3. All right, so we got our ln. Okay, all the values we can represent with exponents to bases have to be greater than 0, right? So we can't take an ln of 0. What exponent can you use to get 0? You can't, nothing. And we can't take ln's of negative numbers because you can't apply a base to with an exponent and get a negative. So anything greater than 0, that's why. Now in this case, x squared is always going to be greater than 0. So the only thing that can't happen is if x is 0. That's the only issue for 39. Otherwise, this will be okay because when you square it, the negatives become positives. And then over here, it's just solving this problem, the expression greater than 0. Now we get to 43 and we got an irrational expression. So this is where you want to use the numerator zeros, the denominator zeros. Again, you don't want to put a 1 under the 0 and cross multiply. That can be problematic. This one you could probably interpret, right? So the only way you're going to get a positive number is if you got a positive 1 over positive. And so the bottom here will start being negative when you're less than or negative 1. So you could think of it that way too. Or you could get your numerator zeros, which there are none. Denominator zeros, negative 1, test points on either side. Okay, so 43, maybe you could have figured it out by thinking. It might have been a little more challenging with D. So if you want this to be greater than 0, you want a positive over positive or a negative over a negative. So again, you can think of it that way. So I use test points on a number line. Numerator equals 0, denominator equals 0. So that's why I got negative 1, 0, and then I just check. Okay, so it was only the right interval greater than 0, the left interval less than negative 1. So that would be the domain. Okay, and then over here, this was a little tricky because you had an outer function. So in addition to the inner function, the x can't be negative or 0. So that's the first inequality statement from the inner function. And then the outer function, you can't take the square root of negatives. So this has got to be greater than, and it actually, oh, this can equal to. It can equal 0 because the square root of 0 is okay. So that's different than the x. So this can actually equal 0 too. Well, what does that mean? The ln means the exponent. So that means the exponent has to be greater than or equal to 0. Well, that means the exponent to the base e, we have to be greater than that. So if the exponent is greater than or equal to 0, then the value is greater than or equal to e to the 0. And that's 1. Anything to the 0 power is 1. Again, this could also be or equal to. So there should be a line under these two statements. Okay, so which one of these is most inclusive? Well, we'd have to accept this one. Because if we accept this one, then there's going to be numbers in between 0 and 1 that'll cause a problem. Because if we put numbers between 0 and 1 in the ln x, we'll get negative exponents. So we pick the inequality statement that's most inclusive, and that would be this one. So, and then again, this is greater than or equal to 1. Should be a line under it. Okay, everybody good? Okay, so time for a quiz. Now, I'm going to go ahead and read out the names of the people who are here just to make sure, and then I'll go ahead and then I'll start emailing y'all one by one. It might take me about 5 or 6 minutes, so I have to do it one at a time. Okay, so I got Patrick, Dimitri, Virginia, Kenneth, Tori, Connor, Miley, Zach, Juliana, Joe, Pierce, Heidi, Catherine, Peyton, Sam, and Christina. I don't think I missed anyone, but I'm just making sure. It's always better to be safe than sorry. Okay? All right, so I'm going to go ahead and start sending y'all the quizzes, and then just get it back to me within an hour. Okay? And I kind of abbreviated it, so I didn't ask you everything, because again, I didn't want to make it too long. All right, y'all. Have a nice weekend.
Thank you, Mr. Napoli. Bye.